Our third technique for evaluating limits algebraically is known as rationalization. Now, as I've said numerous times already, whenever you are evaluating a limit, always begin by trying direct substitution first. And if direct substitution gives you a real number, that is your answer. If, however, direct substitution yields to the indeterminate quotient, which we talked about in the last video, 0 divided by 0 is called the indeterminate quotient, this is a sign that we need to try another technique. If dealing with an algebraic function with radicals, so we have square roots, we want to rationalize our expression. Evaluate the following limit algebraically. Here we have the limit as x approaches 3 of the square root of x plus 1 minus 2 divided by x minus 3. Again, we start by trying our direct substitution. If we plug in 3 for x, that gives us the square root of 4, which is 2. 2 minus 2 gives us 0. We plug in 3 into the denominator, and direct substitution gives us the indeterminate quotient 0 divided by 0. Okay, because we have the presence of radicals, we want to rationalize. And in this case, we want to rationalize the numerator. Rationalization means get rid of the radicals. Well, how do we get rid of radicals when we have two terms? In this case, we want to multiply by the conjugate. We're going to multiply the numerator and the denominator by the conjugate of the numerator. Conjugate means we simply change the sign in between our square root term and our other term. We change the sign in between terms. So we are going to multiply by the square root of x plus 1 plus 2 divided by the square root of x plus 1 plus 2. We are allowed to perform this manipulation because multiplying by this quantity right here is the same as multiplying by 1. We are not changing the value of anything. Now, one thing to make note of, that when we go to multiply out our numerators here, we are going to have to use the distributive property of multiplication. We are going to have to FOIL. Notice that we actually have a binomial times a binomial. Well, when we multiply our first terms, root x plus 1 times root x plus 1, the square root goes away. Notice that's the same thing as squaring root x plus 1, which leaves us with x plus 1. When we continue to use the distributive property of multiplication, we have positive 2 root x plus 1 and a minus 2 root x plus 1. The outer and inner terms of this product are going to add to 0. And finally, we need to multiply the last terms. Negative 2 times positive 2, that gives us minus 4. So we end up with, in the numerator, x plus 1 minus 4. Now, in the denominator, none of the radicals are going to disappear. So we actually don't want to expand that or multiply it out. Instead, leave it in factored form. So we now have the limit as x approaches 3 of x plus 1 minus 4 in the numerator divided by the quantity x minus 3 times the quantity square root x plus 1 plus 2. Again, only multiply and expand out if the radicals are going to go away. That happens in this case in the numerator. Don't multiply out the denominator. It's just going to get even messier. Now take a look at what we have in the numerator here. X plus 1 minus 4. Well, if I take x plus 1 and I subtract 4, that actually gives me x minus 3. And hopefully we see that we also have the exact same factor in the denominator. And so what can we do? We can cancel out that common factor of x minus 3 and simplify the limit. We now have the limit as x approaches 3 of 1, don't forget about the 1 in the numerator, divided by the square root of x plus 1 plus 2. And now we can try our direct substitution again. We plug in 3 for x. Plugging in 3 for x gives us 1 divided by the square root of 3 plus 1 plus 2, which is equal to 1 over 4. Again, we can verify our solution graphically, okay? Here we have the graph of this function. Well, notice there is actually a hole in the graph when x equals 3. But as the x values get closer and closer to 3 from both the left and right-hand side of x equals 3, the y values get closer and closer to 1/4. There is our rationalization technique. Let's try a few more examples. The limit as x approaches 0 of x divided by the square root of x plus 9 minus 3. Again, we try our direct substitution first. Plug in 0 for x. Well, plugging in 0 for x, that gives us the indeterminate quotient, 0 divided by 0. We need to do something else. Notice that there are no polynomials to factor, but we have the presence of a square root. And whenever we see square roots, we want to think about rationalizing. In this case, we want to rationalize the denominator, get rid of the radicals in the denominator. And to do so, we're going to multiply the numerator and the denominator by the conjugate of the denominator. Conjugate means we change the sign in between our terms. So here I have a minus sign in between our terms. We're going to make it a plus sign. We have the limit as x approaches 0 of x divided by the square root of x plus 9 minus 3 times root x plus 9 plus 3 divided by root x plus 9 plus 3. Again, we can complete this manipulation because it is the same as multiplying by 1. Now, in the numerator, we're going to leave this multiplication, this product, in a factored form. Do not distribute the x in because nothing is going to simplify. However, because we're rationalizing the denominator, we're going to end up getting rid of the radicals in the denominator when we multiply. Again, we need to FOIL. Use the distributive property of multiplication. Our first terms, root x plus 9 times root x plus 9. Well, that gives us x plus 9. The product of our outer terms and the product of our inner terms add to 0. And negative 3 times a positive 3 gives us a minus 9. This leaves us with the limit as x approaches 0 of x times the quantity, root x plus 9 plus 3. Notice that we left this in factored form. We did not distribute through. Divided by the quantity, x plus 9 minus 9. Well, we can continue to do some algebraic simplification here. 9 minus 9. Well, 9 minus 9, that equals 0. And at this point, if we try our direct substitution again, we still get 0 divided by 0, but this x and this x are a common factor, and we can now divide those out. So, dividing out the x in the numerator with the x left over in the denominator, and simplifying our limit, we now have the limit as x approaches 0 of the square root of x plus 9 plus 3. Now I have my limit written in a form where I can evaluate it. I can plug in 0 for x. So I try my direct substitution. We have the square root of 0 plus 9 plus 3. That gives me 3 plus 3, which is equal to 6. There we have our solution. Again, we can verify all these answers graphically. Here I have the graph of the function y equals x divided by the square root of x plus 9 minus 3. Notice again, we have the presence of a hole in the graph when x equals 0 here. Well, notice, even with the hole, as our x values get closer and closer and closer to 0, the y values are getting closer and closer to 6. All right, one more here. Evaluate the following limit algebraically. The limit as x approaches 2 of 4 minus root 18 minus x divided by x minus 2. We begin by attempting our direct substitution. We plug in 2 for x, and plugging in 2 for x gives us the indeterminate quotient 0 over 0. Again, we see square roots, and square roots tells us to rationalize. We want to rationalize the numerator here. All right, to rationalize the numerator, we are going to multiply the numerator and denominator by the conjugate of the numerator, meaning we change the sign in between our two terms of the numerator. We are multiplying by 4 plus root 18 minus x divided by 4 plus root 18 minus x. Now, we want to complete our multiplication in the numerator because that's going to get rid of the square root in the numerator. And again, we have to FOIL. Well, we multiply our first terms. 4 times 4, that gives me 16. The product of our outer terms and our inner terms are going to add to 0. If they don't add to 0, we've made a mistake somewhere. So we have 4 times 4 is 16. The product of the inner terms add to 0. And now I have a negative root 18 minus x times a positive root 18 minus x. Well, that's going to give me negative parentheses 18 minus x in my numerator. And in the denominator, we're going to leave this in factored form. We don't want to distribute here in the denominator. All right, we're going to leave our denominator here in factored form because none of the radicals are going to go away. So we have 16 minus the quantity 18 minus x. Again, be very, very careful with your parentheses here. Divided by x minus 2 times 4 plus root 18 minus x. Again, only multiply through, only distribute if the radicals are going to go away. Otherwise, leave it in factored form. Well, let's do some algebra here. Notice that if I am subtracting a negative x, that's the same thing as adding x, so I'm going to end up with an x. And I have 16 minus 18. Well, 16 minus 18, that gives me negative 2. So the numerator actually simplifies into x minus 2. And that is a common factor with the denominator. So what do we want to do with those common factors now? We want them to cancel out. We simplify the limit. Do not forget, when these divide out, we're still left with a 1 in the numerator. This is now the limit as x approaches 2 of 1 divided by 4 plus root 18 minus x. And now we can complete our direct substitution again by plugging in 2 for x. This gives us 1 divided by 4 plus root 18 minus 2. Root 18 minus 2, that's root 16, which is 4, giving us a final answer of 1 over 8. Again, we can verify this answer graphically. Here I have the graph of my function, 4 minus root 18 minus x divided by x minus 2. As my x values approach 2, I have a hole in the graph at x equals 2. But even though there is a hole, the y values are getting closer and closer and closer to 1/8 as x approaches 2 from both sides. All right, so there is our third technique for evaluating limits algebraically. All right, again, we start off with direct substitution. If we end up with 0 over 0 and we see square roots, we want to rationalize either the numerator or the denominator. Get rid of that radical wherever we see it by multiplying by the conjugate. Then we're going to do some algebra to simplify. We should always end up with a common factor between the numerator and denominator that we can then cancel out. If you have done it correctly, this will always happen. Simplify the limit, and then evaluate the limit using direct substitution again.